pipes or pipe flow, whichever way you want to call it. Both the same. It's about liquid. We'll do liquids, but you could apply it to gas flowing through pipes. Also known, you may have heard of the Venturi effect, which we won't get onto, but this is what it's all about really. So pipe flow, liquid through pipes, gas perhaps. So it is relevant to a lot of things, and it's also in an assignment. There's a couple of things we look at. One thing is called mass flow rate, and all mass flow rate is how many kilograms per second, because mass is measured in kilograms and is per second because that's a unit of time. So it's mass flow rate per second. So I get the right thing here. Mass flow rate per second. Now it's m dot or m dash. Don't confuse it with mass. That's why they put a little dot on it. So don't confuse it with mass. It's mass flow rate. Kilograms per second. So it's how much mass per second. For example, you could have, I don't know, 5 kilograms per second, which means there's 5 kilograms of water, oil coming through per second. So mass flow rate. So fairly simple to explain. And the same thing with volumetric flow rate. Volumetric flow rate is just the volume, cubic meters per second. So it's how much volume of water, volume of oil, volume of honey, volume of milk per second. So volume is measured in cubic meters and time is in seconds. So it's volumetric flow rate, cubic meters per second. How much volume per second? Like your blood, your heart will pump your blood around your veins at a certain volume flow rate. V is volume, V dash is volumetric flow rate. So when you see a dash above it, just means flow rate. So mass flow rate is the mass of liquid flowing in a pipe per second. Mass of liquid flowing in pipe per second. So we can look at it like, here's my pipe. Here's my pipe with a liquid of a certain density. Cross-sectional area, so it's the area of the pipe. So in this example, the pipe has got the same area. It's a straight pipe, so there's no change in area. And we're looking at how much mass per second. So if that's a certain mass there, look, this, and this is 1 second. How long does it take for that mass to move through in 1 second? Velocity, right? So obviously this liquid oil has got a speed, a velocity, which we use c. We don't use v because v can be volumetric flow rate. It can be volume, so we don't use v as velocity. In this case, we'll use c because you may confuse it. So it's how much mass of liquid has come through per second. Mass flow rate, kilograms per second. Now there is a way you can work this formula out, but if you go to HNC or further mechanical principles, we'll show you work that out. But here's the formula. So the mass flow rate is density. That's going to be linked to volume, obviously, and mass. So density times by area times by this velocity, the flow velocity. So mass flow rate is the density of the liquid, whatever that is, times the area of the pipe, times by the flow. So density is measured in kilograms per cubic meter. It's mass over volume, if you remember. Mass over volume. Area is just area. So that's a circle. So pi d squared over 4. And c is the flow velocity, meters per second. Because this pipe is the same diameter, the flow velocity will be the same. Obviously, mass flow rate is got to be constant, because we assume that the mass flow rate is constant along the pipe. So it's the same all the way through. If we decrease the area, that's why the speed goes up. If I made this pipe, if I made the outlet, if I tapered it down and made the outlet smaller, the velocity will go up because you've got to get the same amount of mass through per second. That's why if you've got a hose pipe and you put your finger over the end of the hose pipe to narrow the gap of the pipe, the water squirts out faster because there's less area, but the same amount of water's got to get through in the same amount of time. So we're assuming the mass flow rate is constant along this pipe. We're also assuming no friction and that the pipe is full. Obviously, in further studies, we have got friction on this pipe, so the flow is different on the pipe walls because you've got friction. It's like a river. The fastest flow in a river is in the middle because you haven't got any friction due to the side of the river. Same in a pipe. Mass flow rate at the inlet equals the mass flow rate at the outlet. We're assuming it's constant. So the pipe inlet, we know area of the inlet and the flow at the inlet. The pipe outlet, so we've got pipe coming in, pipe coming out. So the area 2 just means the area at the outlet. So this is in, that's the pipe in, and this is the pipe out. So this is the area in, this is the velocity in, and this is the area out, and this is the speed or the flow velocity out. If I had a pipe like this, see, can I not go now? So this is in, and this is out. So the mass flow rate has got to be the same. That's what we're assuming. Now, obviously, the area may change and the flow velocity may change. But we'll assume as well that the density stays the same. Not always the case. But the mass flow rate is the same in as it is out. And we know the mass flow rate is density, area, and speed. So the mass flow rate is density, area in, flow velocity in, density, area out, speed out. So that there has got to be true. This is called the continuity equation. So if you know this, then you can work out stuff over here. For example, if I knew the inlet area and the flow area, and I wanted to work out the outlet speed, and this area changed, then I can use this formula to work that out. It's called the continuity equation. Same thing with the volumetric flow rate, V dash, V dot, volume of liquid flowing in a pipe per second. Same thing, 1 second, cross-sectional area, and that's my C, flow velocity. So here's a volume of liquid, volume of oil, volume of milk, volume of gas coming through, and it's how much cubic meters per second. So how much volume per second. So it's an easier one. You haven't got to explain how we derive this formula, but the volumetric flow rate is simply the area times by the flow velocity. Area meter squared, flow velocity is C. So V dash is area times by C. Area of the pipe times by the flow, this flow here. Again, we've got to assume that the volumetric flow rate is constant along the pipe, just like up here. So the volume flow rate at the inlet has got to equal the volume flow rate at the outlet. So again, here's my pipe. So here's in, and here's out. Mewn a mass. So the area here is A1, and the flow, there's liquid there, look. The flow here is going to be C1. The density, we don't need to worry about. This is going to be area 2. and C2. So whatever the flow rate here is, it's got to be the same over here, because we're assuming the mass flow rate is constant. Mass flow rate is constant. Sorry, the volumetric flow rate is constant. Right? Obviously, the mass flow rate here will be, right, and the mass flow rate here will be the same as well. So the volumetric flow rate is the inlet area and the inlet velocity. That's got to equal the outlet area and the outlet speed. I've labelled them A1 and A2 and C1 and C2. It's just up to you how you want to label them. As long as you know one's in and one's out. So here's the continuity equation for this one. Area in, speed in equals area out, speed out. Because the volumetric flow rate is the same. That's called the continuity equation. Continuity equation. All right. So it also applies to a tapering pipe. Now a tapering pipe is just, it tapers up or tapers down, so you could have one going that way. That's all it is. So, obviously the area there is smaller than the area there. And the area here is smaller than the area there. It's a tapering pipe. So we can apply this continuity equation. Here's our equations, look. And here, look. Mass flow rate in has got to equal the mass flow rate out. M1 is in and M2 is out. Area 1, so area in, area out, speed out. Same thing here. Density will remain the same. So the inlet area is A1, the entry velocity is C1, outlet area is A2, and the outlet velocity is C2. So the mass flow rate here is that, same as before, and the volumetric flow rate is that, because we know the areas, we know the speed. The mass flow rate out has got to equal that, and the volumetric flow rate out has got to equal that. So we know that the mass flow rate here has got to equal the mass flow rate over here, because it's constant. We also know that the volumetric flow rate here has got to equal the volumetric flow rate over here. Continuity equation. No friction, we'll ignore friction, we'll ignore turbulence, no turbulent flow, no turb. Because obviously there's it's not smooth flow in here in real life. Well, depending on the speed it may be, but we're ignoring turbulent flow. It's called laminar flow. We'll ignore friction on the sides of the walls for now. So without needing any numbers, in the above example, which flow velocity would be fastest? C1 or C2? So there's C1 and there's C2. So which one's going to be fastest? Assuming that mass flow rate and volumetric flow rate will be the same. There's a bigger area there, smaller area there. So which speed is going to be fastest? This one or this one? I leave that to you to think about. That is just like putting your finger over a hose pipe. Right? There's less area there for the water to get through, and there's more area there for the water to get through. So have a think about that one. Examples. We'll do some examples because that's why you get a bit of practice. So there will be some questions knocking about, whether they're exactly like this, but I'll give you some practice ones to have a look at and ones to do. So we've got a pipe with a diameter of 50 mil. Let's get some of this going. So 50 mil diameter. It's carrying a liquid density 900. That's my density. It has a velocity of 3 meters per second. Calculate the mass flow rate and the volumetric flow rate. So here's my pipe. It's not a tapering pipe. So it's got 50 mil diameter. 50 mil diameter. 50 mil diameter. Density in there is 900. And the velocity is 3. So the pipe is the same, there's no change in diameter, there's no change in density, and it's 3 meters per second. We need to find the mass flow rate and the volumetric flow rate, nice and easy. Because we need the area, I'll do the area first, look. So we know the diameter is 50 mils, so I'm going to look at the area. So you can use this formula. I would suggest you use that formula. Pi d squared over 4. Don't forget, it's got to be in meters. So 50 minus 3, we'll square that, times by shift pi, divide that by 4, gives you this 1.96, okay, I've just left it there, look, 1.96 times 10 to the minus 3 meters squared, don't forget meters squared. That's my area. Obviously, if you can keep all of this in your calculator, it's a bit more accurate, but I've rounded up or I've left. Yeah, I suppose that's not too bad. So the mass flow rate is just density, area and speed. We know density is 900. We know the area is here. And we know 3 is 3. That's the speed. Seeing I've got the area there, I'll use this number. So we'll get a slightly different number now, because this is going to be a bit more accurate than my number down here. So there's the area. I'll times that by 3. And I'll times that by 900. Gives me 5.3. Let me get rid of that. What am I doing? 1.96 to the 3. Let's do it that way then. Times by 3 times by 900 equals that. 5.292 kilograms per second. That's the mass flow rate. That's how much mass per second is coming through that pipe. 5.292, you could go 5.3 if you wanted to. So tick that one. And then the volumetric flow rate is just that, area times by the speed. Well, we know the area and we know the speed. So 1.96 times by minus 3, because it's here, look. Times that by the speed, which is 3, gives me 5.88 cubic meters per second. So it's not much, because it's only 50 mil pipe. So cubic meter, that's how much cubic meters per second. That's the volume of liquid or the volume of gas. It's probably oil actually. The volume of gas, sorry, the volume of oil coming through per second. Volumetric flow rate, don't forget V dash, V dot, M dot. Alright, not Snoop Dogg, M dog, M dash. So nice and easy, just using that formula. That's all we're going to be using really, is these two formulas really. Number 2, a pipe with a diameter of 10 mil, carrying a liquid of relative density 0.85. Ooh. Relative density of 0.85. If it has a velocity of 1.5, mass flow rate. So mass flow rate is easy. Look, so that's what we've got to do. Obviously, you could work out the volumetric flow rate because it's just A times C in it, but it's up to you. So volumetric flow rate, we need to find the area first. So we know the diameter is 10. So we'll do 10 to get it into meters, look. Like that. Or, don't forget, I'm just doing this. 10 divided by 1,000. Because 1,000 millimeters in a meter. Alright, so like 10 times 10 to the minus 3. Because we're dividing by 1,000. We'll square that and we'll times it by pi, just for a laugh. And we'll divide it. Don't write that answer down. Concentrate, Morg. Minus 3 times by shift pi. Did I square that? I can't remember. 10. Is this lockdown? It's making me go nuts. Squared equals that times by shift pi equals that divided by 4. 7.85. There we are. Press E and G to get it into thing. 78.54. I've gone, look, there's a 9 there, so I've gone to 4 there. That's the area. Square meters. So I know the area now, it's that. I know the speed anyway, because it's 1.5. I know the density. Don't forget, I've given you relative density. So we're going to multiply by 1,000. You should have seen that in previous videos. So it's relative to water, so 0.85. You shouldn't need a calculator to do this. The density is 850. That's the number I'm going to use by there. So the mass flow rate is just all of them numbers times together. So we'll do 850 times by, open a bracket, 78.54 minus 6, close the bracket, times by 1.5, should give me something like that. Dun, 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 dun. Let's do red. Mass flow rate 0.1 kilograms per second. Not much, only 10 mil pipe. So that's the mass flow rate of whatever this is. Kilograms per second. Tick. Down. Down. Very good in Welsh. What's in French? Bon. Number 3, a pipe with a diameter of 30 mil and a liquid flowing through it with a density of 1030. If the mass flow rate of the liquid is 3 kilograms per second, calculate the flow velocity of the liquid. Ooh, alright. So in this one, we got diameter again, 30 mil, so we can do the area here, look. We got density, so we can use a bit of that. That's the number. We're given the mass flow rate, you look. So, and we've got to work out the flow velocity, which is c. I don't like that, I can't really see it. So we've got to find c, basically. We've got to find this. We've got to find that there. We know the mass flow rate, it's 3. We know the density, it's 1030. Salt water or something like that. We know the area because we can work it out. We need to rearrange to find c. So first things first, we'll find the area, pi d squared over 4. You could use pi r squared, but people don't like using pi r squared, because you've got to divide that by 2 and you may forget to do it, and you can't really measure a radius, can you? You could measure the diameter of that pipe quite easily. So use, if you use pi r squared, you just need to remember to convert that into a radius, which you may forget, because some people do. So pi d squared over 4, 30 times 10 to the minus 3 to get into meters. We'll square that. Times it by pi. Divided by 4. Ta-da! Press E and G. 706, I've gone to the 9, look, I've gone up square meters. So that's the area of the pipe. Density, so I've rearranged now. We need to rearrange for C because we don't know what C is. All I've done, I've brought the density and the area down by there. Not by here, by there. So therefore, flow rate is going to be mass divided by density times by area. I've left the C there and brought these two down. So this is going to give us our flow velocity. So we'll do it this way. Let's do this. 3 divided by, let's overkill again on the brackets, times by 706.9. You could go to 707, couldn't you, if you wanted to? close, close, come over here, equals 4.12 meters per second. So it's flowing along this pipe at 4 meters per second. 4.12 meters per second. Now you can check this, make sure you spell check correctly. We could check this now because we know that the mass flow rate is density, area and speed. Now we know the mass flow rate is 3. So to check my speed, if I pretend I didn't know what that m was, like I'm doing here, look. So if I put my number, this 4.12, if I put this 4.12 back into this formula to see if I get 3. Are you with me? So the mass flow rate is density, area and c, which is velocity. So 1030 times by that times by 4.12. Now if I get 3, which I do, roughly, I know I'm correct. So just one way of checking that everything is right to a certain extent. Obviously, because I've rounded things up and we've done things like that, that's measured exactly 3. But it gives you a good indication that your work is 3, look. 3 in my eye. So 3 kilograms per second. So I'm fairly confident that that is correct now. Flow velocity of the liquid, there we are, cool. So that's just rearranging that formula a bit. So nothing strange, nothing new. Number 4 is a tapering pipe. It's just a pipe, look. And it's starting off big and it's going small. So there's my pipe. So it starts off, we've got an area here of 0.08 and we've got a I thought 4 was the last one. Area of 0.08, so I've given you the area, here's my speed, there's my density of my liquid. I know the outlet, so the area is getting smaller. I don't know this speed, I need to work it out. Now, it's very similar to the one I asked before. Which speed is it going to be faster than 0.5 or less than 0.5? Don't forget, we've got less of an area, so the mass flow rate is the same, so it's got less of an area to get out. So the same amount of liquid's got to come through here as it is here. So it's got to get faster because there's less of an area for it to get out. If it's 3 kilograms per second here, it's got to be 3 kilograms per second here, the mass flow rate, which means hopefully C2 is going to be bigger than C1 because the mass flow rate is the same. That is exactly like putting your thumb over the end of a hose pipe. But first of all, we're going to look at the mass flow rate. Now we know the mass flow rate here is going to be the same as the mass flow rate here, because we'll assume that. So if I can work out the mass flow rate here, I can then work out the velocity here. So I'm going to work out the mass flow rate using this number, and this number, because I know all the correct numbers. So mass flow rate, density, area and speed, we know the values for the inlet, so it's going to be the inlet mass flow rate, which will be the same as the outlet mass flow rate. But I know these numbers, don't know these yet. So density is 1020, the area in is 0.08 and the speed in is 0.5. So density is 1020, delete that side, so again, density is 1020, the area is 0.08 and the speed is 0.5. Gives me that 40.8 kilograms per second. So we've got 40 kilograms, 40.8 kilograms coming in there, which means we've also got 40.8 coming out of by there. That's why the speed should go up, because you've got the same amount coming through but less space to fit it in. So it's got to get faster. So I know the mass flow rate is 40.8 each side. I know the mass flow rate is constant. So mass flow rate in has got to be the mass flow rate out, 40.8. So I've got 40.8 coming in, 40.8 coming out. So here's my formula. So I know the mass flow rate coming in. I know the density of the water. It's 1020. And I don't know the speed. I'm trying to find the speed. So I know this, but I don't know this. So I'm going to rearrange a formula to find this. I'm just going to bring to there. So I'm going to bring density and area down, just like we did up here somewhere. Right. So mass flow rate divided by density times by area. That's my mass flow rate because we've worked it out. The area is 0.02. The density is 1020. So that divided by that. So 40.8 will come down here. We'll do divide that by, let's put a bracket on this, 1020 times by 0.02. Close that. We go to there, press equals 2. So tick. So it's 0.5 has gone up to 2, less area. Now 0.08, 0.02, so there's a ratio here that you may see, 0.5, so you can work it out that way if you want to do. Because it's getting less by a certain amount, which means, but we've worked it out, so 2 meters per second. So obviously it's got to get faster, it's got to be 2, because it's got to be higher than that in it, because you've got less area. Tick. This makes sense. As the pipe area decreases, the velocity must increase. Same amount of liquid must get through in the same amount of time. So there we are. Makes a bit of sense. Always think about your answers, see if they make sense. Number 5. Again, inlet and outlet. Diameter 30 mil. Speed in is 2. Density is 1020. The speed out is 50, but we don't know the pipe diameter. Calculate the outlet pipe diameter. So if you were working in an oil factory, an oil somewhere, or a water factory, or a, not a water factory, you know, like a milk factory, milk processing, oil refining, and you wanted to work out the pipe because you knew the speed perhaps. So we need to calculate the outlet pipe diameter. So again, I'm going to work out the mass flow rate here, and I'm going to work out the mass flow rate here first. I can do it here because I know the area and I know the speed. Once I know the mass flow rate, I can then use the formula, and then I can find area. Because I know the speed over here, I know the density. If I can find the area of this, if I can find A2, I can then work backwards to find diameter. Because I know area is pi d squared over 4. First things first, work out the mass flow rate this side. I know what it is. It's going to be density, area, and speed. Find the area here first. So A1 is going to be 30 mil. So we'll do 30 minus 3. We'll square that. Times by shift pi. Divide by 4. Press that. So 706.9. Like that's the inlet area. Inlet. That's the area coming in. So now we'll work out the mass flow rate coming in. We know this formula. The density is 1020. The area is this. And the speed coming in is 2. So I'll keep that number because it's a bit more accurate. Times that by 2. Times that by 1020. equals 1.44 kilograms per second. So that's the mass flow rate coming in. That's going to be the mass flow rate coming out. So I've got 1.44 here, which means I've got 1.44 coming there. Everyone's a winner. So now I know the mass flow rate out, because I do, it's going to be 1.44. I know the density of the water is 1020. I don't know the area, I know the speed. If I can find the area, if I can find A2, I can then use pi d squared over 4 to find diameter, because that's what area is. So if I can find A2, I can then use this to find D. Are you with me? So rearrange this formula to find A2. So all I'm doing is bringing the density down to there and the speed down to there. Gives me that. So the mass flow rate, which I know is 1.44, the density I know is 1020, and the speed out is 50. That will give me the area. So it's there. So I'll leave that number in, 1.44. We'll divide all of that by 1020 times by 50. So 28.2 times 10 to the minus 6. You could even do a bit more if you want to. So that is area 2. So the area on the out, this is A2. So 28.27 to the minus 6 is the area coming out. So I know the area is pi d squared over 4. And I know the area is this. So all of this has got to equal pi d squared over 4. So the first thing I'm going to do is bring the 4 up here. So 28.2 times 10 to the minus 6 times by 4 equals pi d squared. Then I'm going to bring the pi down to here. I'll bring the pi down there, which gives me that. And then I'm going to square root all of this to get rid of that. So 28.2 times 10 to the minus 6 times by 4 over pi would equal d squared, and then square root all of that to get the answer, to get d, diameter of the pipe. So it's getting faster, so we would expect, it's 2 there, so it's getting faster, so we'd expect this to be less, wouldn't we? Which it is, right? So work it out. So let's do it this way. Let's make sure careful. So let's overkill 28.2 to the minus, so that's 6. We'll close that. Times that by 4, say, close that and close that, come down here, all divide that by shift pi, and if my brackets are correct, dun, 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 there we are, 5.99 times 10 to the minus 3 meters, so 6 times 10 to the minus 3, which is 6 mil diameter. In it, really? That's meters there. So nothing wrong with that answer, but if you want to put it into millimeters, because like 6 divided by 1,000 gives me, there we are. So the pipe here, to get a speed at this end, we need to have a 6 mil diameter pipe. Now, we've ignored things like length of pipe and friction of pipe. If this pipe was 60,000 miles long, it's a different story, isn't it? If you're piping oil from the North Sea to Scotland, you know, the pipes are long, so it's not as easy as that, because you've got friction and you've got pressure losses and things like that. But first, for now, that'll do. 6 mil diameter. Have a go at them, please. I will put some of the questions on Moodle for you or something. So There's only a few formulae we're using, so it's not that terribly difficult. So enjoy pipe flow. Over and out.